the greater the bulk of substituent or substituents near the OH group of alcohol or the COH group of acid, the slower is the process of esterification. This is called steric hindrance. Therefore, the rate of esterification decreases in the following order: methyl alcohol, then ethyl alcohol, then 2-methyl ethanol, then 2,2-dimethyl ethanol. In the same manner, formic acid, acetic acid, 2-methyl propanic acid, and so on. Aromatic acids having no group in their ortho positions can be readily esterified with alcohols in presence of some mineral acids like HCl, H2SO4, HNO3, etc. The reaction is C6H5COOH plus C2H5OH in presence of mineral acid as described above or as described earlier gives ethyl benzoate C6H5COO2H5 plus water. Here water is a byproduct formed during the reaction. However, if an ortho substituent is present, then the rate of esterification greatly decreases due to the same steric hindrance. Thus, the esterification of the various benzoic acids follows the following order, like benzoic acid, then 2-methyl benzoic acid, then 2,6-dimethyl benzoic acid, then 2,6-dimethyl phenyl acetic acid. The substituted phenyl acetic acid is easily esterified because COOH group or carboxyl group is separated from the benzene ring by CH2 group. The ortho substituted benzoic acid can be easily esterified by treating the silver salt of the acid with alkyl halides. This is due to the fact that in such cases the attack of alkyl moiety of the alkyl halides is on the oxygen atom of COOH or carboxyl group, but not on the sterically hindered carbon atom. The reverse reaction of esterification is known as hydrolysis, which may be effected by acids as well as alkalis. Hydrolysis of ester in presence of alkali is commonly known as saponification. Mechanism of esterification is already discussed in alcohols, but remember that the mechanism of ester hydrolysis is exactly reverse to the mechanism of esterification. Mineral acids speeds up both processes by protonating carbonyl oxygen and therefore rendering carbonyl carbon more susceptible to nucleophilic attack. In esterification, the nucleophile is an alcohol and the leaving group is water, while in ester hydrolysis, the nucleophile is water and leaving group is alcohol. When both of the functional group, that is hydroxyl group, the OH group, and the carboxyl group, the COOH group, are present in the same molecule and separated from each other by 3 or 4 CH2 group, then cyclic esters, which are commonly called lactones, having 5 or 6 membered rings are formed. This is called intramolecular esterification. One example of intramolecular esterification is the conversion of 5-hydroxy-butyric acid to 5-pentanolide. Now, the next chemical property of carboxylic acid is the reaction with phosphorus halides or thionyl chlorides. The thionyl chlorides are the compounds containing sulfur, or in general the compounds having sulfur are called thiocompounds. The reaction is when acetic acid or ethanoic acid is treated with PCl5, the phosphorus pentachloride in presence of pyridine, then acetyl chloride CS3COCl is formed along with the liberation of HCl and PuCl3. Here pyridine is used as an organic solvent. The next reaction is CS3COOH, ethanoic acid, when treated with SOCl2, the thionyl chloride, in presence of pyridine, then again acetyl chloride CS3COCl is formed along with the liberation of sulfur dioxide gas and HCl. However, thionyl chloride SOCl2 is found to be very convenient as the side products are gaseous and the excess of SOCl2 can be easily removed as its boiling point is low, which is 79 degrees centigrade. The reaction of carboxylic acid with thionyl chloride SOCl2 is SN2 type, H sulfur atom, in which Cl or chlorine is the leaving group.